Alright, let's continue. Okay, so wait a minute. Introduction to operating system. If you are taking an undergraduate operating system course, you should already have some idea of what a computer does when it runs. If not, some idea of what a computer program does when it runs. If not, this book and the corresponding course is going to be difficult. Okay. So you should probably stop reading this book and run to the nearest bookstore and quickly consume the necessary background material before continuing. Okay. What a computer program does. Okay. Alright. So what happens when a program runs? Well, a running program does one very simple thing. It executes instruction. Right. All of this code is some kind of instruction. Okay. Many millions, and these days even billions of times every second, the processor fetches an instruction from memory, decodes the instruction, figure out which instruction this is, and execute it. Okay. It does the thing that it is supposed to do, like add two numbers together, access memory, check a condition, jump to a function, and so forth. After it is done with this instruction, the processor moves on to the next instruction, and so on until the program finally completes. Okay. Thus, we have just described the basic of the von Neumann model of computing. Oh, I didn't know about the von Neumann model. Okay, sounds simple, right? But in this class, okay, we will be learning that when a program runs, a lot of other wild things. A lot of other wild things are going on with the primary goal of making the system easy to use. Right. Simple does not mean easy. No. Usually something easy to use is not simple. Usually there is a body of software. In fact, that is responsible for making it easy to run programs, even allowing you to seemingly run many at the same time. There is a body of software that is responsible for making it easy to run programs, allowing programs to share memory, enabling programs to interact with the device, and other fun stuff like that. That body of software is called operating system. Okay. Wait, let me check the footnote. Of course, modern processors do many bizarre and frightening things. Underneath the hood to make program run faster, executing multiple instructions at once, and even issuing and completing them out of order. Okay. This one, out of order stuff, can cause a problem. Like this. What is it called? Race condition. Something like that. But that is not our concern here. We are just concerned with the simple model most program assume. With the simple model most program assume that instructions seemingly execute one at a time. Okay. Because if I remember correctly, let me put this in here. We will also taking a look at concurrency. This one. So for now we do things in the, what is it called? In the serial order. One at a time. Something like that. In an orderly. Okay. I thought I was disconnected. Okay. My internet connection still fine. For now at least. In an orderly and sequential fashion. Okay. This is the one. The sequential order. Right? But then in the next section or next piece, we will be talking about concurrency. Okay. Von Neumann was one of the early pioneers of computing system. He also did pioneering work on game theory and atomic bomb. Oh, okay. And played in the NBA for 6 years. What? Okay, one of those things isn't true. Which one? Which one? Okay, the crux of the problem. How to virtualize resources. One central question we will answer in this book is quite simple. Wait a minute. Maybe I need to Maybe I need to take notes. Oh, this one. One central question: how does operating system virtualize resource? Right? Like the virtual memory and stuff. This is the crux of our problem. With the OS does this is not the main question. It makes system easier to use. Oh. Okay, so by virtualizing resource make the system easier to use. The how? Let me take notes. Why? Virtualize resource. How the operating system virtualize resource? What mechanism and policies are implemented by the operating system to attain virtualization? How does the operating system do so efficiently? What hardware support is needed? As a way to call out specific problems we are trying to solve in building an operating system. Thus, within a not on particular topic, you may find one or more classes. Is that how to pronounce this? Yes, this is the proper plural. Okay. Let's highlight the problem. The details within the chapter, of course, present the solution, or at least the basic parameter of solution. Okay. That body of software is called operating system, as it is in charge of making sure the system operates correctly and efficiently in an easy-to-use manner. The primary way the operating system does this is through a general technique that we call virtualization. That is, the OS takes a physical resource and transform it into a more general, powerful, easy-to-use virtual form of itself. Thus, we sometimes refer to the operating system as interesting. Referring operating system as virtual machine. Okay. And well, I think this is kind of new for me. I mean, I know about the virtual memory, right? A little bit about virtual memory, but then it turns out we also virtualize the CPU. Yeah, and maybe even a disk too. That is interesting. Okay, let me take note. Okay. One. The primary way the operating system does this is through a general technique. Yes, virtually. To make the system easier to use. It means that operating system takes a physical resource such as the processor, or memory, and transform it into a more general, powerful, and easy to use. Sita is virtual form of itself. Thus we sometimes refer to the operating system as virtual machine. And thus make use of the feature, the virtual machine, the operating system, okay? Of course, in order to allow users to tell operating system what to do and thus make use the features of the virtual machine, such as running a program or allocating memory or accessing a file, The operating system also provides some interface API that we can call. Okay. A typical operating system, in fact, exports a few hundred system calls that are available to application. Because the operating system provides these calls to run program, access memory interface provide these calls to run program, access memory interface, and alternated action. We also sometimes say that OS provide a standard library to application. Okay. Finally, because virtualization allows many programs to run, to sharing the CPU. Sharing the CPU, okay. And many programs to concurrently access their own instruction and data to sharing memory, and many programs to access the files, to sharing text and so forth. The operating system is sometimes known as a resource manager. Let me take notes of that. Operating system is sometimes known as a resource manager. Virtualization allows many programs to run sharing the CPU. concurrently access. One instruction. Instruction and data. Transferring memory. And menu book. Access to files. The operating system is sometimes resource manager, sometimes known as resource manager. Each of the CPU, memory, and disk is a resource of the system, right? It is thus the operating system role to manage those resources to ensure efficiently or fairly, or indeed with many other possible goals in mind. To understand the role of the operating system a little bit better, let's take a look at some examples. Where is the footnote? Oh, this one. think this is the, what is it? Body of software. Okay. It's called operating system. Another early name for the operating system was supervisor, or even the master control program. Oh, interesting. Apparently the letter sounded a little overzealous. Okay. See the movie Tron for that. I haven't seen this movie yet. And just thankfully, operating system got on instead. Alright. Okay. This is the example, right? Standard input output, standard library, I guess. System. Oh, okay. Assert in the current directory common.h. Okay. Common. Main. Okay, argument count and argument vector. Okay. Not equal to usage CPU string. What? Okay. Oh, we need to provide an argument string for this CPU script, I think. And then this one, right? Argument vector. Get the, what is it called? The first argument, because the index 0 is the name of the script, like this. So we took the index 1, put this in here, str, spin. Oh, interesting. Is this the syscall, system call? Let me check. No, okay. Yeah. Nothing. Maybe this is from common header. I'm not sure. And what this pin supposed to do? Print. So we are printing the first argument over and over again. Is that it? Got that loops and print. Oh, got that loops and print. Okay. Write the name of the script. CPU.c. Virtualizing the CPU here in this one. Okay. Figure 2.1 depicts our first program, it doesn't do much. In fact, all it does is call spin. And what is spin? A function that repeatedly checks the time and returns once it has run for a second. Oh. Is it similar to sleep? Maybe. And returns once it has run for a second. I'm assuming the second is the argument here. So maybe if we provide 2, it will return after 2 seconds. Maybe. Okay, and then it prints out the string that the user pass in on the command line and repeat forever. Yeah, because of this, like there is no precondition. Like when should we stop the iteration? So it repeats forever. Let's say we save this file as CPU. Say we save this file as cpu.c, okay, and decide to compile and run it on a system with a single processor. And run it on a system with a single processor, or CPU as we will sometimes call it. Okay. If I remember correctly, CPU stands for Central Processing Unit, something like that. Well, you can take a look, I guess. Okay, on the search engine or something like that. Here is what we will see. We compile, right? Oh, the book also add the flag W all. Interesting. Okay, this is the binary result name. This is the script, and well, this is the compiler that we use. So we run something like this. It will print out until we use Ctrl+C to interrupt the program, right? Okay, and there is no precondition with this while loop, so we need to interrupt it because it repeats forever, right? Okay. If we didn't interrupt this program, it will repeat forever. Okay, it's not too interesting of a run. The system begins running the program, which repeatedly checks the time until a second has elapsed. Once a second has passed, the code prints the input string passed in by the user. For example, the letter A. Okay, because of this, we need to use exactly 2 arguments for the program. So if we do something like this, it should be an error too, right? Because it is not 2 but 3. Not this one. 1, 2, and 3. 3 argument count. Again, the first argument or index 0 is the name of the program, this one. Okay, Once a second has passed, the code prints the input string passed in by the user, the letter A, right? This one. So if we change this to P, we will print out P instead. And continues, not the program will run forever, right? Will run forever. By pressing Ctrl C, this one, the symbol, usually in the terminal, the caret means, or this one, means control, and C is, well, the C character, so Ctrl C. And if I remember correctly, there is no difference whether we use uppercase C or lowercase c, as far as I remember. Okay, which on Unix-based system. Yo, how old are you? Why do you need to know my age? That is a secret. Okay, which on Unix-based system will terminate the program running in the foreground. Which on Unix-based system will terminate the program running in the foreground. Okay, yep. This one, the Ctrl C1, okay. We can halt the program, right? Unix-based system. This is another example, but we are putting the process in the background instead of the foreground. Right, something like this. This is, what is it called? The process ID, something like that, IP. And yeah, interrupting this will be a lot harder. Now let's do the same thing, but this time let's run many different instances of this same program. So the result of this slightly more complicated example, yeah, just likely, right? Well, now things are getting a little more interesting. Even though we have only one processor, somehow all four of these programs seem to be running at the same time. Somehow. How does this magic happen? Well, this one running in the background, right? As far as I understand, does this magic happen? Check the footnote 4. Okay. It turns out that the operating system, with some help from the hardware, is in charge of this illusion. With some help from the hardware, it's in charge of this illusion. The illusion that the system has very large number of virtual CPUs. Oh. Turning a single CPU or a small set of them into a seemingly infinite number of CPUs, and thus allowing many programs to seemingly run at once, is what we call virtualizing the CPU. Okay. Virtualizing the CPU. The seemingly run at once. So of course, to run program, use single CPU into a seemingly infinite number of CPUs. Okay, of course, to run programs and stop them, right? And otherwise tell the operating system which program to run, there need to be some interface, the API. Okay, application programming interface. I kind of forgot what the API stands for. Basically, we need some interface to use in our program, right? That you can use to communicate your design to the OS. Okay, so the operating system also have an API. In case anyone didn't know, we will talk about this API throughout this book. Indeed, they are the major way in which most of users interact with operating system. You might also notice that the ability to run multiple programs at once raises all sorts of new questions. For example, if two programs want to run at a particular time, which should run? Okay. The policy of the operating system. Which should run? Right, we have two programs, right? At a particular time. I think this means the order the program should run. Maybe the policy of the operating system. Policies are used in many different places within the operating system to answer this type of question, and thus we will study them as we learn about the basic mechanism that operating system implement, such as the ability to run multiple programs at once. Used in many different places within an operating system. Policies, okay. The basic mechanism. Run multiple programs at once. Hence the role of the operating system as a resource manager. At the same time, by using the ampersand symbol, right, this one, the user runs a job in the background, in the cell. You don't need to use ZSH to use this symbol. You can use base, dash, or maybe other cell. And I'm not sure, is this POSIX standard? Maybe. Yeah, I mean, I'm not sure if the fish cell have this symbol too. I mean, in case anyone knew, fish cell. This is what I mean. The fish cell is not POSIX compliant, thus not following the POSIX syntax. So I'm not sure if fish have an ampersand symbol. Okay. Which means that the user is able to immediately issue their next comment, which in this case is another program to run. If you're using a different cell, okay. It looks slightly differently. Oh. Okay. Looks like not a cell have the ampersand symbol to run the process in the background. Interesting. I never tried TCHH, so I don't really know. But yeah, I know that TCHH is another cell, at least. Read documentation online for detail. Alright. Hello. Sichan, welcome. Okay. We're currently on chapter 2, I guess, this one, the introduction of the book called Operating System 3 Easy Peasy. This one, ostep.org, if you want to take a look. Okay, include UniSTD, input output, leave common. Okay. Oh, wait a minute, let me check. We didn't have UniSTD. Okay. But what we replacing? System. Oh, maybe the spin is from the sys time heater. Maybe. I mean, I never tried this. What is it? Library, I guess. So I didn't really know. UniSTD, okay. Use malloc. Alright. Asset p not equal null. Okay. Printf address pointed to by p. Okay. This is the memory address, get PID. Okay. Is get PID in this header? This is the PID and this is the memory address of the pointer. What? Oh, okay. Right, we are using integer. Okay. We are still doing this. Okay. It will run forever again until we interrupt with Control C. Okay. This one, the reference, okay, and put this in here, right? Get PID, Oh, E1, E2, E3, E4. That access memory mem.c. Okay. Virtualizing memory. Wait, let me check. Get PIT. Okay. Oh, we use the system call manual, right? This one. Oh, okay. That's why we need UniSTT header. Alright. Return to process IT. To PIT, right? PIT stands for process IT of the calling process. Generate unique temporary file name. Okay. Set access memory. Now let's consider memory. The model of physical memory presented by modern machine is very simple. Memory is just an array of bytes. To read memory, one must specify an address to be able to access the data stored there. To write or update memory, one must also specify the data to be written to the given address. An array of bytes. Okay. Wait, is this the physical memory or the virtual memory? Or maybe both? Okay, the model of physical memory by modern machine is very simple. So, yeah, I'm not really sure. Let me take notes. Memory is just an array. Array of bytes. Array of bytes. Okay. To read memory, one must specify an address to be able to access the data stored there. To read call it memory. Okay. One must specify an address. To be able to access the data stored there. To write or update memory. We must specify the data to be written. Written to the given address. The given address. Okay. Memory is accessed all the time when a program is running. A program keeps all of its data structure in memory and access them to various instructions like loads and stores. When the program is running, A program keeps all of its data structure in memory and access them through various instructions like loads and stores or other explicit instructions that access memory in doing their work. Don't forget that each instruction of the program is in memory too, right? The instruction itself is in memory too. Thus memory is accessed on its instruction fetch. Take a look at the program calling malloc. Okay, the PID is the same. The process ID, okay. This is the memory address, right? And now we are running this in the background too. Okay. See, the process ID is kind of different. Oh, hold on a minute. Okay. The memory address is the same for different, what is it called? Different process, right? I think this is the virtual memory that we are gonna discuss. The program, okay, running the memory program multiple times. The program does a couple of things. First, it allocates some memory and A1. This one, right, using malloc to allocate the memory. Wait a minute. Okay. Then it prints out the address of the memory into the printf statement. Okay. And then puts the number 0 into the first slot of the newly allocated memory, A3. Where is it? This one. We are accessing the memory in P and then put 0 in there. Okay. Finally, it loops, delaying for a second and incrementing the value stored at the address held in P. Delaying for a second and incrementing the value stored at the address held in P. Delaying for a second, write the spin. This one. But yeah, maybe spin is not coming from the system header here. I mean, yeah, where are we using this? What library do we use this for? Interesting. Okay, and then spin. Oh, not that one. Okay, this one. Delaying for a second and incrementing the value stored at the address held in P. With every print statement, it also prints what is called the process ID or identifier, right? The PID, process identifier, or people just call it ID, right? Of the running program. This PID is unique per running process. Unique per running process. Again, this first result is not too interesting. The newly allocated memory is at address this one. As the program runs, it slowly updates the value and prints out the result. Now we again run multiple instances of this same program to see what happened. 2.4, this one, right? We see from the example that each running program has allocated memory at the same address, right? This one, even though the process is different, right? As the program, okay, and yet it seems to be updating the value at 0x 200,000 independently. It is as if its running program has its own private memory instead of sharing the same physical memory with other running programs. Indeed, that is exactly what's happening here, as the operating system is virtualizing memory, right? So what is it called? Making to isolate, maybe that's the word. To isolate its process, something like that. Each process accesses its own private virtual address space, sometimes just called its address space, which the operating system somehow maps onto the physical memory of the machine. Okay. Yeah, I'm still not sure. I mean, there is a virtual address and also virtual address space. What is the difference there? With the OS somehow, with the operating system somehow maps onto the physical memory of the machine. A memory reference within one running program does not affect the address space of other process. To itself. Okay. What the operating system itself, as far as the running program is concerned, it has physical memory all to itself. The reality, however, is that physical memory is shared resource managed by the operating system. Exactly how all of this is accomplished is also the subject of the first part of this book on the topic of virtualization. For this example to work, you need to make sure that the space randomization is disabled. Okay, randomization as it turns out can be a good defense against certain kinds of security flaws. Read more about it on your own, especially if you want to learn how to break into computer system via stack smashing attack. Not that I would recommend such a thing. Not that we would recommend such a thing, okay. Let me take note of this. Process has its own access. Is owned by virtual address space. The space sometime got it as with the operating system. Maps onto the physical memory. Physical memory of the machine. The machine a memory reference within one running program does not affect the address space of other process. Memory reference Memory reference within. Within one running program. Does not affect the space. The space of other processes. The operating system itself. The physical memory is a resource. Topic of virtualization, okay, and then concurrency. Right. Okay, maybe we will take a look at this in the next session. So what field are you going into? I'm trying to learn about system programming. So yeah, that's what I'm aiming for. Okay, we will continue this on the next session. So I think that's it for now. Thank you for watching and see you next time. Bye bye.